So it's an abbreviation for first time right. So I came across this in one of a previous conversation with a client where they were listing down the SLAs, and this was mentioned as one of the points in the SLA that any bug that we encounter in production should be fixed in the first attempt. Right? We cannot take multiple attempts to fix a bug. Right? And if we do that, then there will be penalties that will be raised on because of that. And this sounds too obvious to be coined as a term, right? If you have a bug, you can fix it, and that's going to work in the first time, right? But what's so special about it, right? And if you have to fix a bug, one of the important things that you need to have is this. Do you want to take a guess? Second entry. No, but that's a close. But that's close. So if you have a bug card or you open it, what is it that you look for in that card? Reproduce. Yeah. So that's the steps to reproduce. Right. So you need to know when a bug happens. What is the context? What is the preconditions that you need to have? And what are the exact steps that you need to take? And what is expected? What is actually happening? Right. So this gives a very clear and objective description of the bug. And once we have it, fixing it, reproducing it, fixing it, and then verifying the fix is all going to be a cakewalk, right? But then comes a special type of bugs called Heisenbugs, right? These bugs happen only in production, right? We would do the testing in local work, we do it in multiple environments, things will work. But when you ship it in production, it will happen once in a while, or it might happen very rare, right? But it will happen, and it's very hard to reproduce this, and it's very hard to have a mental model around why such things happen in production growth, but not in lower environments. These are very uncertain, and it's the unicorns of a unicorn of unicorns of sort, and that's why we call it as Heisenbugs. And then we can fix these bugs, right, by speculating about what could have gone wrong when such a thing happened. We could go through the logs and traces, and we can figure out what might have gone wrong. We could have fixed it, but there are certain side effects of fixing these bugs, right? One is we don't know whether we fixed it for sure because we don't know how to actually confidently reproduce the bugs, right? So that will reduce the confidence of the team itself. So as a dev, would I have confidence in saying the clients or customer that having fixed this bug? I wouldn't, right? Because I don't know. I think I have applied a fix, but there could be multiple layers of it. Like I might have fixed only the surface of it, whatever was on the first layer, and maybe once that is fixed, the other work that is beneath it might surface again, and that could be that would reduce the confidence of the team. And when as a client or the end user, when they are looking at using your product or using your services, it wouldn't have a good impact on it, right? So let's say we have a product, a user encounters a bug, and we say that they have adjusted, but the next time they try, they see the bug again. It would reduce the confidence, and they will eventually walk out. And the last thing is that it will also make the code messy, right? Since we can't, uh, we don't know why such things happens. We tend to get into the mode of defensive coding, right? And there will be, you can see all sorts of methods that span across hundreds of lines with multiple if conditions, and no one has a clear idea about why such a condition. Would know if I remove it, what will fail, right? And that means that nobody would dare to touch it and clean it up. Right? It's not just in the code, right? There could be other architectural elements, like say a job that runs once a month, and you don't have any context on what it does. You stop the job, you don't know what is going to break, right? So that makes the entire architecture and the code at a messier pace, right? Which is not a very great state to be in. So today, let's look at or let's break down the complexity of distributed systems. right? And this Heisenbugs is a concept that is borrowed from the distributed system world. So let's look at what brings complexity to distributed systems, and what are the different Heisenbugs that you can have in distributed system space, and what is the role of DST in finding and fixing those bugs. And then we'll shift to the microservices world and see how we can abstract that concept and apply it for microservices in Node. So when we talk about distributed systems, there are two primary sources of complexity. Right? One is their concurrency, and other is the distribution. Right? Let's take an example, and maybe we can go through it and understand how each of these things add complexity to the system. So let's consider two processes, right? Very simple ones. Each of the process has only three steps, right? ABC and XYZ. So if we execute them in sequence, we can be pretty confident about what's going to happen next, right? Let's say if we execute P first and then Q next, this is going to be the sequence in which the commands will be executed. The only other possibility is that Q comes before P, which will be XYZ and ABC, right? This is very simple, and this is the state where we were before distributed systems came into place. This is everything runs on a single computer on a single threaded way, and things were pretty simple. Then if we introduce concurrency within these 6 different steps, there could be multiple combinations in which these execution can happen, right? And we can't predict what is going to be the exact sequence of steps when we execute these statements, both the processes in parallel, right? And if we add distribution to the mix, we can't predict what's going to fail next, right? So within that 20 different steps that we saw, it can fail at any point, right? It can fail from the beginning or after a few steps, or it might even complete the execution, right? So if you look at the sequence of steps, right? So from a basic and simple execution of 6 steps, we have now come to like 60 plus different combinations in which things can happen, and some of it can be failures. And it's not that, so most of the time, so there is also this Pareto's principle that comes into it, right? Majority of the time, things are going to work, right? And there is a 10% or 20% of the combination which is going to fail, and the possibility of us hitting that particular combination that fails is going to be very rare, right? And that is the breeding space for these Heisenbugs. And this particular explosion, where we went from 6 to 60 different combinations, is called behavior space explosion, right? Now, if you consider hundreds of processes with each of them with multiple steps, then we cannot hold all of them in our head, and we will not be able to even list down all these combinations. And it's not going to be humanly possible. So this explosion of the behavior space is where the Heisenbugs become very rare to spot, and because of the nature of this space, it becomes very hard to reproduce as well. So you'll see the bug the first time. You run the same thing, but it'll pass. Things will work. So you'll not be able to confidently reproduce what went wrong. So this mandates that we should have a testing mechanism which can span across space and time. So when we say traces, it is the number of steps in each of those different combinations, right? So we should be able to test almost all of those possible traces, and we should also be able to test as many number of unique traces as possible, right? It's not just that the number of traces is important; it should also be able to identify different steps and more number of steps in each trace. Right now, I mean, in the example that we saw, we had only 3 different steps, which will, at the max, you will have 6 different steps. But that is not the case for a practical distributed system. That you need to scale across both these phases, and that's where DST is actually helping them in, satisfying both these conditions. Right? Let's take a quick look at how it does it. This is a very simple model of any software system, right? You give an input, it does some processing, and you get the output. And this application is the system under test. And any application doesn't sit alone, right? It sits in an environment. Right? There are things around it at a OS level or at a system level, which influences the way the application behaves when it is deployed in that particular environment. And if we are able to control that environment and make it deterministic, then we will be able to verify the different traces that comes out. For example, if for deterministic simulation testing to work, the combination of this application and simulator has to be unique and deterministic, in the sense that I should be able to control the simulator in a way that for a given setting, it will always produce the same output for the same input. Right? So that's what makes it deterministic, and to be able to write such a simulator, right, we need to have it needs to satisfy these 3 different properties. We should be able to virtualize the environment, because we cannot actually run it on a real environment, because things are not going to be in our control in a real environment. So we need to have control over the environment, and we need to have control over the kind of failures that we want to inject, right? So again, it kind of ties back to the first one, because if we run it in a real environment, we have no control over what will fail. So we need to be able to virtualize it and be able to inject failures at a given rate, and do that in a pseudo random fashion. Right? So it cannot be completely random, because if it is completely random, things are not in our control. So it needs to be a pseudo random system. Okay. So let's keep this in mind. We will probably come back to it when we do the simulation and see how we can use each of these properties for the benefit of testing microservices. So this is where we are right now, right? So we looked at what makes distributed systems complex, and we looked at where do Heisenbugs lie, and what is the role of DST in taming these Heisenbugs. Now we'll shift gears and we'll go to the microservices. This is a very familiar picture. So if we imagine distributed systems as a connected set of computers over the network, we can apply the same parallel to microservices. So just that we have broken down the monolith into independently deployable components, and each has its own each runs in its own containers, and each has its own DB, right? And since the microservices inherit or take inspiration from distributed system, they also inherit the sources of complexity, right? So thereby, it is also concurrent, it is also distributed. So the same problems that occurred in the distributed system world is going to happen in microservices world as well. And we have seen it that those things happen. So the problem of concurrency in a distributed, microservices world is that each service will either be driven in events, or it will be responding to requests, and these can arrive at different point in time, and we can receive duplicate events, and it's not just because of the nature of the services itself, right? We use a lot of distributed system for building our microservices. The DBs that we use are now horizontally scalable, and they are distributed. And we might even use some messaging systems like SQS or Kafka, and those are distributed in nature. So the combination of all these things will make sure that these things happen in when you actually apply and run these things in production. And the race conditions can emerge between services. In let's say in distributed systems, if race conditions emerge across threads, here it will emerge at a different level of abstraction, and it will happen between services. But it will eventually happen. Okay? And when we have distributed it, the so the or it's also pros and cons in the sense that you can have one service, you can afford to have a service go down while the rest of the services are still up and running and serving the customer. But it can also be a source of problem for us, right? That any service can go down at any point in time. And because of the network nature, it can introduce latency or it can drop packets and you might not receive the messages in time. And because of this, we are forced to add other architectural elements to ensure that we should be able to retry in case of a timeout or be able to have a circuit breaker. Let's say something is a dependent service or a upstream service has gone down, and it shouldn't take all the other services along with it, right? So we need to have some sort of circuit breaker in place so that we can have some back pressure and survive even in the case of other services failing in an architecture. And since each of the services are split and isolated, we also have the problem of distributed transactions. So in the monolith world, everything was in the same DB, and the databases ensured that we had ACID property, and that will ensure that everything happens at all or none. But since we have broken it down, and it is an induced complexity that we have created for ourselves, that anything that was happening in a single and simple transaction is now split across multiple services, and the onus is on us to ensure that the integrity is still maintained, right? An order cannot be created when a payment has failed, or an order cannot be fulfilled if the inventory has no stock. And so these are things that should be in sync, and we need to handle those, and we need to accommodate for all these things by means of compensating actions. Saga is one of the most popularly adopted pattern that can help us deal with distributed transactions. So we will look at an experimental setup, right? And see what can go wrong in a controlled environment, and see how we can make use of a simple simulator to find a bug and then reproduce it and fix it. Okay. So this is a typical setup that we've seen in any microservices example, right? So let's read it one more time. We have a card that kind of acts as a orchestrator. So when we check out a card, it will create an order and it will initiate a payment. Simple. And this is how a happy path looks like, right? Things will work most of the time, and when we do demos, it will work. And it might also fail at times, right? So you initiate, the order is created, but when you initiate the payment, that might fail or that might time out. So in a sense, we want to retry or time out, right? And when we do that, we should make sure that we are not charging the customer twice. So that's the basic funda that we pick up, and let's see how we can simulate it and fix it. And these Heisenbugs do not happen because a single particular service is buggy, right? So in the example that we saw, each of the service is doing and fulfilling its own responsibilities in the right way, right? So card is supposed to initiate both the order creation and payment, and that is doing that. Order service is supposed to create an order. It does its job perfectly. Payment is supposed to initiate a payment through the payment gateway, and that does its job. But when we put these things together, that is where the bugs come in, right? Because the sum of all parts is not equal. The whole is never equal to the sum of all of its parts. It's always greater than that. And the bugs are not actually in the logic, right? If we test the services for functional completeness, they work fine. But the bugs are in the timing of the messages. It's in the timing of the messages, the order in which these messages arrive at different phases. Uh, and it also depends on, no, it's actually in the interleaving of these different methods and requests where these bugs actually lie out. And how are we dealing with these in the current state, right? So we have a spectrum of test strategies that we now adopt, starting from the traditional test layers, right? So when I say traditional test layers, it includes all sort of unit and integration tests, contract tests, or end-to-end tests, automated, everything else, right? These tests are highly reliable, right? You can run them on the CI/CD pipeline, and it will give you the right feedback on whether the business logic is satisfied or not. And then on the other end of the spectrum lies the chaos engineering setup, which gives us the feedback on whether the application is resilient enough or not, right? Let's say we unleash the Simian army and it will go down and pull all the flags, and your system should be able to come bring it back up and keep things up and running. And the the deterministic simulation testing is the sweet spot that kind of sits in between, which should ensure the reproducibility of traditional test layers and also test the resiliency of the system in a controlled environment. So we looked at the properties of a simulator, right? So just to recall, it should be virtualizable. We should be able to virtualize the environment. We should be able to inject failures at a controlled manner and drive things in a pseudo-random fashion. So in the setup that we are going to see, we are using test containers for virtualization. Right? I think test containers, we don't have to introduce that. I think it's a widely popular library today. And then we use ToxiProxy to inject failures. ToxiProxy is a library which can inject different kind of failures in the network layer, right? So it can sit in between services and act as a proxy, and it is toxic in nature. So there are different types of toxicity that you can add to it. It can be latency, or it can drop packets at random. So there are multiple different ways in which you can configure the toxics, and it will act accordingly. And pseudo randomness, we have the Java's old Java random. So this is how the setup changes from the typical setup. We now introduce two different proxies that sits in between the orders and payment services. So yeah, so this is the setup where have the card service, payment, and order service, all three of them Dockerized, and so I have set up the ToxiProxy, and I have started all these three services uh, here. And we would run the simulation, say, multiple times. And here, for the sake of showcasing this ability, we'll run this, just the 10 times. So when we run the simulation, these are the things that we are doing, right? So if you back, so we use this as the iteration as the seed for each particular simulation, and that is what we pass to random. right? So Java's random library by nature, if given a seed, it will always produce the same set of sequences. So, and using that, we will get a latency for payment. We will introduce a latency for order service, right? And then we will check out the cart, and we'll kind of add whether simulation errored out in between or did it complete. But once it completes, we'll need to check whether the number of orders created and the number of payments initiated match each other, right? And once everything is done, we can tear off all the toxicity that we have added. So that's going to be the setup for this simulator, right? So let's run this once. So it has now started running the simulations multiple times. So it's going to execute the same scenario, but like you can see, the card was checked out in different times. So sometimes it was, in hundreds of milliseconds, sometimes it was more. And we can see that duplicate payments were charged in these two simulations, right? So the good thing is if we are able to run the simulation with these two as a seed, right, any one of them, it will always be reproducible, right? So let's try that as well. So let's try 9. And let's run the test again. Right. So irrespective of, how many however number of times you run this same simulation with the same seed, it's going to fail, right? That is a given. So how do you think we can fix the double payment issue? What should the payments service do to not charge the customer twice? So it should know that it has already raised payment for this particular order, right? So it needs to maintain a state, and it should ensure that if the payment has already been charged for this customer, it shouldn't retry payment for that. And that particular, so if it is able to maintain that state, irrespective of how many number of times we call payment, we initiate the payment, it will hit the service, but within the service, it wouldn't initiate the call to the payment, right? So this property has a name. So it's called idempotency, right? So it should not have any side effects, and it should only be charged once, right? And idempotency is a very important property for microservices, especially when we deal with such retries and other conditions in place. So to help us, I have also fixed the payment service and expose the environment variables so that we can just control it from the test here without going through, building the service all over again. So now we think we have fixed the bug, right? Let's run the simulation and test it out. All right. So now the card has been checked out, but there are no failures, meaning no duplicate payments. So let's also see if the other one, we had two failing conditions, right? Yeah, let's also see if all of these simulations will prevent, just to ensure that we are not introducing a new bug while fixing. Right? So, so they have now fixed the bug. We can confidently shift this to prod. Yeah. So let's go back. So this is the key for developing and deploying any software, right? So we need to be very certain uh, that things work in the way they are expected to work, and that is what is what will help us confidently say develop and deploy any system in production. And DST can potentially help us achieve this level of certainty by methodically exploring this behavior space. So in this example, we were able to set up latency as one of the toxicity between two different services, and we are able to spot a particular Heisenbug, right? But if we are able to run different simulations, we right now ran only 10 different simulations. I think in a actually complex software, there will be more number of different states to be checked, and we will have more hypotheses to be ensured from the business side, right? We need to let's if we add just inventory to the mix of this, we can ensure that inventory shouldn't be double booked, right? And we shouldn't be creating orders when the stock runs out. So there could be multiple different business cases that we need to ensure, and we should also be able to check different states in time when there are n number of microservices in picture. Any thoughts? Have Have you seen this in your day-to-day life, or and do you think this can help, or do you think this would not work? We have seen this and state management. We haven't cut all the possible factors at times. There is more complex. So, other than finding particular factors, and we will be fixing that addressing it. So, what probably, how can we be sure about how to find all the possible, pretty complicated in the state of adjustment related management, and there is another and multiple microservices. And how can we be so sure about this particular kind of events? So idempotency is not a silver bullet for fixing things, right? So when we say that idempotency can help in this case, even after introducing idempotency, things can still break. Um, let's say that in order to maintain idempotency, you need to do the state management, right? And how do you do state management? You need to process things in the DB problem. Right? What if the DB to application communication happens? What if that breaks? Right? So we haven't introduced the toxicity at the application to DB level. Right now, the toxicity that we have introduced is only between the service to service communication, right? So maybe what we can do is to increase the uh, number of different layers where we can inject toxicity. I think so. When we spoke about the behavior space explosion, we spoke about two things, right? One is the number of traces that we want to capture, and the number of different steps in each particular trace, right? So if you in the current one, the number of states is only three, right? Card is checked out, order is created, payment is initiated, right? And then after we fix it, we let's say if we add another layer between the DB and application, the number of steps will actually increase, right? So when you say the card is checked out, the call to the order service is made, and then the order is actually persisted in the DB, and the response is sent out. So that the one step will now be broken down into three different steps. The same thing will happen for payment service, right? So it receives the request that will be captured as one step, then persisting it in the DB, and then sending out a response will be considered as three different steps. If you make it much more granular, we should be able to introduce more such toxic points where we can inject those failures, and then we'll be able to capture things where let's say even if in the even in the presence of idempotent services, things can still go wrong, and we'll be able to capture this. So I think we haven't explored. And this setup, I don't know if there are the primary challenge with DST today in microservices is that the lack of tooling. Right? So this toxic proxy is a thing that can inject failures into the network. But network is not the only component, only non-deterministic component in the architecture, right? That could be we are deploying the application in two different services. Let's say their clock goes out of sync, right? So, and if you're dependent on, say, the creation time or timestamps to determine, whether order is created first. In the case of the inventory double, right, the timestamps are going to be important. And if the clocks are not synchronized, things can break there, right? And we don't have, I don't know if we have tools that can inject or simulate system clocks in a reliable manner, right? So in the absence of those things, I think simulating more such failures for microservices is going to be challenging. But that is something that we can look out for um, and keep adding to the simulator toolkit as and when we come across those levels. Yeah.
Replicate of the entire production. But the issue is replicating the entire fast.
Right.
How we should handle the better. Can you visualize the production environment is much more difficult for the data for the properly test. And we are replicating.
So it depends on whether you treat the data as part of your application or as part of your environment, right? So I think it also ties back to this question on how do we handle the cases even in the presence of state management, right? When we look at the payment service as a whole, the app and DB are packaged together, right? And we assume that it's going to work. But when we break them down, DB becomes part of the environment, and talking to the DB is one of the points of failure that can potentially happen. And in your case, we need to have some data setup. I think that's also so. In this case, it was a pretty simple one because we just had to write a order ID and we could do that. But going by the traditional testing principles, right? A test shouldn't be dependent on the data access. Any test should be able to set up its own data and run its set of sets and clean up the data as well.
because of the data, production level data.
Yeah, because of the nature of data that is there in production.
Production working perfectly in staging. Comes to production level, so what's happening with the data production. So
yeah, so for that, I think we can synthetically generate the data for staging environment. So there are tools that are available which can look at your production DB and it can, you know, infer the some insights about the data from a statistical perspective, right? Let's say if, let's say that you have a string column where you are capturing the name, right? And it can look at, let's say if you have thousands of records and say only 500 of those records have a name, right? And it can capture that as a statistic and it can replicate it can generate synthetic data that matches the statistical properties of your prod DB, right? So it's called the synthetic data generation, and there are multiple tools out there because for the data engineering space, I can give you that. I don't remember this from the top of my head, but there are multiple tools, and for data engineering, this is one of the key aspects because they cannot have all the production data to run all their experiments on. So they need to have a synthetic data vault. I think synthetic data vault is right, where you can you don't have the exact replica of your prod data, but you do have the data set which exhibits the same properties as that of your prod data. So that's something that we could use. So if you folks want to get more know more about deterministic simulation testing, so these are some of the references that I've provided. So all of these are from people who actually practice this in their day-to-day work, right? So there are so there is a Bill Wilson was the founder of Antithesis. He was earlier with Foundation DB, which actually practiced introduced DST in its at least a decade before we do. And we need to they offer this as a service where you can ship them their your containers and they will run it in their simulated environment. They're completely virtualized it. I haven't looked at how they managed to do all those things, but uh, it will be run in a very controlled environment where you could also simulate clock level or multiple network level OS level dependencies. And most of it is from the distributed system space, and most of it is from people who develop DBs, Tiger Beetle, Foundation DB, etc. But those are really interesting ideas which could be borrowed to the microservices world.